Hello everyone, welcome to KTU Classes. In this video, we'll discuss another problem of our substitute frame methods. This is our second problem, and please do watch the first video in order to understand the various loading conditions for corresponding moment at certain spans, etc. First video is necessary. It is a theory video, and then we are moving on to problems. And I'll give the link of the same in the description box below. Please feel free to watch. So this is our second problem. In this, they have asked us to analyze a frame for beam negative support moment at B. That is, we will have to get a maximum negative support moment at B, and it is given that the moment of inertia of the beam is 1.5 times of the column. Let's consider that the moment of inertia of the column is I and the moment of inertia of the beam is 1.5 into I. And the total dead load is 14 kN per meter and total live load is 9 kN per meter. So our ILD will be something like this. In order to get a maximum negative support moment at B. So let's get started. So first we'll have to draw a substitute frame, and we'll have to load, not to get a sagging moment at AB and BC, we'll have to load the live load in the span AB and BC. That is what is done here. The dead load 12 kN per meter. 14 kN per meter is loaded throughout the span. That is this blue color loading, and the live load is 9 kN per meter, which is loaded only in the span AB and BC in order to get a maximum negative support moment at B. And the next step is to find the fixed end moments. As you all know, the equation for a fixed end moment when it is a UDL is WL square by 12. If it is the left support, it is minus WL square by 12, and it is the right support, it is WL square by 12. Therefore, FPM AB equals minus WL square divided by 12, which is equal to minus 23, which is 14 plus 9 into 6 square, the length, divided by 12. Similarly, FBA equal to WL square by 12, which is equal to 69 kN meter, and FPM-BC equals 23 into 4 square divided by 12, and FPM-CB equal to plus WL square divided by 12. And similarly for the span CD. Then what is our next step? Next step is to find the distribution factor. In order to find the distribution factor, we need the stiffness coefficient. Stiffness coefficient equals 4EI by L. So, we know that the moment of inertia of the column is I, and the moment of inertia of the beam is 1.5 times of I. Therefore, what will be the stiffness coefficient of AB? K equals KAB, consider this is KAB, is equal to 4 into EI. E is constant into I is 1.5 I by 6. Similarly, for KBC will be 4 into 1.5 IE divided by 4, and CD will be 4 into 1.5 I divided by 4. And for the column, it will be the length of the column is 3.5 meter. Height of the column is 3.5 meter. Therefore, the stiffness coefficient for the column will be 4 into E into I divided by 3.5. So see, corresponding 4EI by 3.5 for the column, AB is the beam, and it is 4E into 1.5 divided by 6, and A2 is the column, 4EI by 3.5. Similarly, for all the members, the stiffness coefficient K is calculated, and then the next step is to find the total stiffness sigma K. That is the sum of the stiffness at a particular joint. If we consider joint A, we have this column, then this column, and this beam. So the sum of the stiffness coefficient will be stiffness coefficient of A1 plus stiffness coefficient of AB plus stiffness coefficient of A2, which is 23 EI divided by 7. And then the next step is to find the distribution factor, which is K divided by sigma K. If we consider AB, K is 4EI into 1.5 divided by 6. Sigma k equal to 23 EI divided by 7. So, when we apply this equation, we get 0.304. And similarly, we'll have to find for all the numbers. We'll have to calculate the distribution factor. And then the next step is to draw the moment distribution table and calculate the final moment. So, we have joined A, B, C, D. Members AB, BA, BC, CB and DC, and the distribution factors of these members are also given and also the fixed end moment. Then the first step is to balance the moment. Now to balance, here we have minus 69, so we multiply 69 into 0.304 and we'll get 20.976. And in the joint B, we have 69 kilonewton meter and also minus 30.67 kilonewton meter. So what we do is that we add. When we add, we get 38.33 kilonewton meter, which is negative. We take the positive value, 38.33 into 0.209 will give us minus 8.01 and 0.313 will give us minus 11.997 as our answer. Then similarly for C, we have 30.67 and minus 18.67 at the joint C. On addition, we get 12 kilonewton meter, which is positive. We'll take the negative. If it is positive, we'll take the negative. If it is negative, we'll take the positive value. We take the positive value, that is 12. 12 into, we get 30.67 minus 18.67, we'll get positive 12 plus 12. We'll take the negative value, that is minus 12 into 0.284 will give us minus 3.408 and minus 12 into 0.284 again it will give us minus 3.408. And similarly for DC, considering DC, there is only one member that when considering joint B, there is only one member, that is DC. So we'll directly multiply this fixed moment with the distribution factor and we'll get the value minus 7.393. Then the next step is carryover moment. So 20.976 divided by 2, 10.488, and then minus 8.01 divided by 2 will get minus 4.005. Then minus 11.997 divided by 2 will give us minus 5.998 and minus 3.408 divided by 2 will give us minus 1.704. And then again minus 3.408 divided by 2 minus 7.393 divided by 2. And then again we'll perform the same balancing operation once more. And then again carry over moment, and then we'll calculate the final moment. Here we have only calculated the final moment for joint B, since that is what is asked in the question. Hope you all understand, which we'll have to calculate for joint B, that is 69 minus 8.01 plus 10.488 minus 1.836 plus 0.608 will get 70.25, and similarly minus 30.67 minus 11.997 minus 1.704 minus 2.749 plus 1.376 will give us 45.744. Then the next step is that we draw the span, and we have a 70.25 kilonewton meter acting clockwise and a 45.744 kilonewton meter acting anti-clockwise. So which one is the greater? 70.25 kilonewton meter. Therefore the maximum beam negative moment at B will be 70.25 kilonewton meter. This solves the problem. See, pretty simple. All you need to know is the loading condition and how to find fixed moment. Then we'll find the distribution factor, and then from the moment distribution table find the final moment. That's all. So thank you. Please share, like and subscribe to this channel. We'll be coming up with more videos. Thank you.